Hello class, in this lesson we're going to talk about radioactivity and we're going to focus on the nuclear force. So I'm just going to mention the four fundamental forces here. So the four fundamental forces, this would be a review. So the four fundamental forces that we have looked at in the past, you know about the gravitational force. So there's gravity and there's the electromagnetic force. Then there's the weak nuclear force and the strong nuclear force. So radioactivity, we are going to focus on the nuclear forces. Okay, so just a quick review here for the four fundamental forces. Gravity, the agent of gravity is mass. So you have mass, you have gravity. Electromagnetic forces is the charge, and weak nuclear forces, the particles that act on the weak nuclear force. The particles that act on the weak nuclear force are called leptons, and the strong nuclear force acts on particles we call quarks. We're not going to be going into so much details about the leptons and the quarks. Okay, so in this section, we are going to look at, state what particles the strong nuclear force acts on, which are quarks, why it is necessary, and the range over which it is effective. It only acts over very short distances. It is the strongest of all the four fundamental forces, but it acts only over very short distances. So they have to be very close, which makes sense because atoms are very, very small. Whereas gravity, compare that to gravity, gravity is quite weak and the weakest of the four fundamental forces, but the most dominant of the four, because all you have to have is mass and it acts over a very long distance. So what happens when the number of neutrons change? Then you're looking at isotope. If the number of protons change, then you have basically a different element. So you can actually have the same number of proton in an element, but if the neutron changes, you still have the same element, but you now have what we call an isotope. So more details on that later. We're going to look at what is radioactivity, why does it occur, what are the radiation rays, alpha, beta, and gamma. We're going to look at transmutation, and we're going to define and calculate binding energy and mass defect, and we're going to convert units of energy in terms of joules, EV, and mega EV. So let's take a look at radioactivity and radiation. There is a limit to how large a nucleus can be before it becomes unstable and break apart. So if you look at the periodic table of the elements, which I'm going to attach to the blog, as the element becomes larger, they will have more number of electrons also increase, and that's what the atomic number means. It's increasing number of protons, which is equal to the number of electrons. They become very unstable because the number of orbital shells increase and they become farther away from the nucleus. And as you recall, what happens is with force, the relationship is force is inversely proportional to the distance square. So as the number of shells increase, and you have the proton here and the neutron, positive and negative there, proton and neutron, the number of electrons, as you have more orbitals because of the increase in electron, there will be weaker attraction between the electrons and the nucleus itself, and they can that will decrease, that will make the atom unstable. So as more and more protons make up a nucleus, there comes a point when a balance of repulsive electric forces and the attractive strong nuclear forces can't be achieved by an increased number of neutrons. So the atom will become unstable, and it is this instability that causes radioactivity. So this spontaneous disintegration or rearrangement of the nucleus is called radioactivity, and it was first discovered in 1896 by Henri Becquerel, a French physicist. And then in 1898, Marie Sklodowska, who later became Marie Curie, married to Pierre Curie, discovered and isolated two highly radioactive elements called radium and polonium. And polonium named after Marie Curie's birthplace, Poland. And radium because it is radioactive, which of course they didn't know about the dangers of radioactivity until later. And an interesting fact also about Marie Curie is that all her manuscripts, all her work, and her remains actually is encased in lead case. Her body is buried with a lead coffin because of the radioactivity in her body. There are three kinds of rays that are produced naturally, and these are called alpha, beta, and gamma. They are named according to the first three letters of the Greek alphabet. If you look at the comparison between the three types of ray, you have the alpha, which is the weakest of all, and it can actually be blocked by a sheet of aluminum foil. So if you have a single aluminum foil, that will protect you from the alpha waves already. So this is the weakest. Even your clothing and paper can partly block alpha rays. Then you have beta, and beta is stronger than alpha. It can penetrate to about 0.1 millimeters of lead and several millimeters of aluminum. These two are particle waves or particle rays. The last one, gamma, this is the most penetrating. This is the strongest of all the three rays. And this is not a particle. This is pure energy. This is energy that is not a particle, so it has no mass. It can penetrate 2 kilometers of air or 100 millimeters of a thick sheet of lead, so it's very strong. As a matter of fact, gamma is used in a lot of medical procedures called gamma rays or gamma knife, and you can perform surgery with a gamma knife without incision, without cutting through the body of the patient. And it can direct the rays quite precisely and used in surgeries in tumors, for example. If you direct it and calculate it precisely, you can perform a surgery without having damage to the surrounding tissue, as in a scalpel surgery. So it's very useful in medical physics. So if we look now at energy and frequency relationship, the gamma ray is a high frequency, very short wavelength, and it is a form of electromagnetic radiation. So it doesn't have a mass or an electrical charge. I'm going to elaborate a little bit on the electromagnetic radiation here. If you were to look at a wave, and I'm going to just start with the one with the longest wavelength, and I'm just going to freehand draw this. So here is a wave that is going to be tighter. Try to. There's my freehand version of an electromagnetic wave. So this is my EM wave, or the electromagnetic spectrum. So I'm going to start with the one with the longest. As you can see, the wavelength here. This would be a little bit of a review from Physics 30S on the unit on wave that you looked at. I'm going to put a review on this in the blog as well. So here is the one. This is a wavelength, one from here to here. This is 1 lambda, so one wavelength like this. So this is called the equilibrium, right in the middle. So the state of balance right there. And you have one wave when you go from equilibrium to the second equilibrium. And as you can see, this is the one with the longest wavelength. The length of the wave is long, but the frequency is how often in 1 second, how many waves are you going to get? So this is one wave. Compare that to the opposite end. This is very short wave. So this is the one with the shortest wavelength. Now the wavelength has a symbol of lambda, the letter L in the Greek alphabet. I'm just gonna focus this a little bit here. So this is the one with the shortest wavelength. And being a shortest wavelength, there will be more frequent waves traveling per second. So this is the shortest wavelength with the highest frequency. And this would be the one with the lowest. I meant to write this with the lowest frequency, and this is the highest frequency. So we could say then that the relationship between frequency and wavelength is the, why is this? There we go. The frequency is proportional to 1 over lambda, meaning that the longer the wavelength, right here, the lower the frequency. We could also now add here that frequency is proportional to the energy of the wavelength. And there's this is an idea that came from Max Planck and gave us the Planck's equation. One of the most important and actually the foundation of quantum mechanics, Max Planck, is based on this relationship. Frequency is proportional to the energy level, and frequency is inversely proportional to the wavelength of the wave. So I'm going to put the names. I'm going to name the electromagnetic spectrum here. And this would be the radio wave right in this end. So let's say this is the radio wave. And this would be where the microwave is. So let's say that's the microwave. And this would be the infrared right here. And this is the visible light. And as you can see, the visible light is just a part of the electromagnetic spectrum. Most of it we actually can't see. In this visible light spectrum, this can be broken down into the colors of the rainbow. So you have red, orange, yellow, green, blue, and violet in that frequency, from low frequency to the highest frequency. Visible light, and then you have your ultraviolet, UV light. So let's say here, this is the UV, this is the X-ray, and this would be the gamma ray. So this is what we were just talking about minutes ago. The gamma ray is the highest frequency, therefore the highest energy level on the electromagnetic wave spectrum. And how I remember this, by the way, is RMIV-UXG. RMIV-UXG. So the first letter of each one is that's how I remember it. So from longest wavelength, the lowest frequency, to the highest frequency. And the visible light, this is the spectrum. That kind of tells you also why is the rainbow red at the top. So here is red. See if I can I can put the if I can find the colors here. So red, orange, yellow, green. There's my green, blue, and violet. So why is the color of the rainbow always red at the top? Well, now you know, because of the frequency and the wavelength. So you see red is the one with the longest wavelength. So the arch is not as tight as the violet, being the highest frequency and therefore the highest energy level. So if you were to have a lightsaber, what would you pick? The violet colored lightsaber or the red colored lightsaber? I'll go for the violet. Okay, the one with the highest energy level. So that is gamma energy there with the highest frequency and the highest energy level. Transmutation is defined as the conversion of one chemical element into another. So transmutation is the change in the structure of the atomic nuclei and may be induced by a nuclear reaction. So this could be a neutron capture, or it can occur spontaneously by radioactive decay, such as an alpha and a beta decay, which are the particle decay. So in transmutation, the nucleus is changed. This is not a chemical reaction. A chemical reaction, recall that it is the number of electrons that can either be gained or lost. In this case, it is the number of it is the number of the nucleons, which is the number of neutrons. Chemical reactions involve change in the outer part of the atom, the region where electrons are found, whereas in transmutation, it is in the nucleus where change occurs. So that is what happens in transmutation. We're going to look at alpha, beta, and gamma reactions in a separate lesson, more specifically, and we're going to learn how to balance an alpha, beta, and gamma nuclear reactions in my next lesson. But let's just take a look at the mass defect of the nucleus and nuclear binding energy quickly, and we're going to address this also in more details. So the nucleon, now again, what does the term nucleon mean? Just a quick review here. According to the Bohr model, you have the proton and the neutrons within the nucleus, and then in the shells in the outside, which if I suggest you watch the video on what an atom really looks like. In the more basic science courses that you've taken, you may have been very familiar with the Bohr model of the atom with the nucleus and the orbital shells being nicely concentric circles around the nucleus, and you can count the number of electrons and the number of shells, with the first shell having 2 electrons maximum and the second shell having 8 electrons and so on. Well, the atom actually does not look like that. The orbital shells, the electrons, are more of a clouds of probability. We actually can't really locate them if we know their momentum, and if we don't know their location, we can calculate their speed. Anyway, that is another pretty complicated quantum theory. We can talk about that later. So here in the clouds of probability, in the where the electrons are, here are the protons being positively charged and the neutron having a balanced number of positive and negative charge. The term nucleons is basically the proton plus the neutron. That's all that is. That is what that means. The more stable the nucleus is, the greater the amount of energy required to break it apart. So if you have a very stable nucleus, let's take a look, for example, at hydrogen. In hydrogen, you only have, here is the nucleus of hydrogen, you have one proton, you don't even have a neutron. So hydrogen has zero neutron in its stable form. So you have one electron right there. So this is what hydrogen looks like. The more stable the nucleus is, and that's a very stable nucleus, then you have more energy required to break it apart. That makes sense, because if you have a high force, if you have a big force holding it together, then you're going to need a large amount of force to break it apart as well. The binding energy of the nucleus is the energy required to break it apart. So you could also look at it as the energy that is holding the nucleus together will be equivalent to the amount of energy required to break it apart. And this is known as the binding energy.